Hey everyone, and welcome back to this class, the Numpy stack in Python. In this lecture, I'm going to show you some other matrix operations that Numpy contains. I'll assume you're already familiar with these from your linear algebra studies, so this is more like showing you how to do those things in Numpy. First up is the matrix inverse. So let's first create a matrix. So the inverse function is in the linalg module. So A inverse is equal to np.linalg inverse of A. So that's A inverse. We can check that the inverse has been calculated correctly by multiplying A inverse by A. So that's A inverse dot A. That gives us the identity matrix. We can also try A dot A inverse, and that should also give us the identity matrix. Next up is the matrix determinant. So that's np.linalg.det of A. So that gives us -2 as expected. Sometimes you want the diagonal of a matrix. So that's np.diag of A. That gives us the diagonal elements in a vector. Other times, you have a vector of numbers which represents the diagonal of a matrix, and all the other elements are assumed to be 0. To actually represent that as a 2D array, you can call the same function. So for example, np.diag of 1, 2 means 1, 2 goes on the diagonal, and everything else is 0. So you want to remember this rule. If you pass in a 2D array to diag, you'll get a 1D array of the diagonal elements. If you pass in a 1D array, you'll get a 2D array where all the off diagonals are 0, and the original array takes up the diagonal. Sometimes you have two vectors and you want to do an outer product. One place the outer product shows up is when you're calculating the covariance of some sample vectors. We've already seen the element-wise product, which is an asterisk, and the dot product, which is the dot function. Recall that the dot product is also called the inner product. So let's make two vectors. A is 1, 2. B is 3, 4. So the outer product is np.outer AB. So you can check that that's correct. Note that we can also do the inner product with np.inner. So this gives us the same thing as A.B. So it's up to you which one you want to use. Another common operation is the matrix trace. This is the sum of the diagonals of the matrix. Note that we can already do this using what we know so far. So that would be np.diag of A, and then we sum everything. That gives us 5 as expected. But Numpy gives us a direct function to do it also. So we can call np.trace of A, and we also get 5. The last thing we'll talk about is eigenvalues and eigenvectors. If you don't know what these are from linear algebra, you probably have some more theoretical studying to do. But this is just going to show you how to do it in code. So you can skip this if you don't know what eigenvalues and eigenvectors are. Often, we want to compute the eigenvalues and eigenvectors of a symmetric matrix, like the covariance matrix of a dataset. So let's create some random data. So 100 by 3 of Gaussian distributed data points. Notice that the convention is that each sample takes up a row and each column is a feature. So for this particular fake dataset, we have 100 samples and 3 features. Of course, Numpy comes with a function to calculate the covariance already. So let's try that. So np.cov of x. Let's just check the shape of cov to be sure that it's correct. So cov.shape is 100 by 100. This is the wrong shape. We expect our covariance to be 3 by 3, since our data has 3 dimensions. So let's try that again with the transpose of x. So now cov is 3 by 3. So you want to remember when you calculate the covariance of a data matrix, you want to transpose it first. Now there are 2 functions you can use to calculate the eigenvalues and eigenvectors, eig and eig-h. Eig-h is for symmetric and Hermitian matrices only. If you've never studied linear algebra with complex numbers, don't worry about what a Hermitian matrix is. A symmetric matrix is a matrix that is equal to the transpose of itself, and a Hermitian matrix is equal to the conjugate transpose of itself. We know that the covariance is a symmetric matrix, so we can use eig-h. So let's try that. Okay, so this gives us a tuple. The first tuple contains 3 eigenvalues. The second tuple contains the eigenvectors stored in the columns. Now let's try this with just regular eig. Okay, so we get the same answer. Notice that the regular eig function gives us the same answer, but the resulting eigenvalues and corresponding eigenvectors can be in a different order. This particular time they were not, but it is possible for it to happen. Alright, so that's it for this lecture. It moved pretty quickly because it was designed for people who are already familiar with the math concepts, but might not know how to do them in Numpy yet.